Welcome to our video lecture on ionic bonding and covalent bonding. Our essential ideas for today. Ionic compounds consist of ions held together in lattice structures by ionic bonds. We will talk a little bit about what even is a lattice structure in a couple more slides. We're going to also look at covalent compounds and how they form by the sharing of electrons. Our objectives for today, we are going to define ions and ionic bonding, and then we're going to review how to name ionic compounds, nomenclature of ionic compounds. Then we're going to do the same thing for ionic bonding, and we'll review how to name those guys. We're going to draw some Lewis structures of covalently bonded molecules, which will help us understand the relationship among bond order. That's like single, double, triple bonds, and the length of the bonds and the strength of the bonds. We will review by comparing and contrasting ionic and covalent bonding. We'll talk about how we can categorize those different kinds of bonds by looking at differences in electronegativity, and then we will wrap up our day with a review of how do we name acids. Good, so first up, ions. What even are ions? Ions are formed when one or more electrons are transferred between atoms. So ionic bonding is all about the transfer of electrons. We have a couple different kinds of ions. We can have cations or anions. Cations are positively charged. Usually they are metal ions that have been oxidized. And so you can remember this, when you lose electrons, that's oxidation. Losing electrons is oxidation. Leo is the nice mnemonic device there. Anions are negatively charged, usually non-metal ions that have been reduced. When we gain electrons, that's reduction. So you can remember Leo says Ger, lose electrons, oxidation, gain electrons, reduction. You can also use this mnemonic device, oil rig, where oxidation is the loss of electrons, reduction is the gain of electrons. What's kind of nice about oil rig, even though I think lions are way cooler than oil rigs, oxidation is the loss of electrons or protons. And sometimes we forget that oxidation can be about the protons, reduction is the gain of electrons, or can be the gain of protons. Good. Either way, Leo says Ger, oil rigs, oxidation is losing, reduction is gaining. Lose electrons, oxidation, gain electrons, reduction. Have that memorized. All right, so let's talk about the formation of an ionic bond here. Electrostatic attraction forms between oppositely charged particles. So we're going to start with a sodium atom. It's got that one valence electron, which makes it quite unstable. It's going to transfer it over to the fluorine atom, which now becomes fluoride. The loss of an electron by the sodium is oxidation. It results in a positively charged cation. Fluorine gains that electron, that's reduction, results in a negatively charged anion, and then those opposites attract. Sometimes I say it's kind of like a magnet. Oppositely charged particles are attracted like magnets, but this vocab, electrostatic, is much, much better. So we can talk about the electrostatic attraction between the oppositely charged ions. That is an ionic bond. This is sodium fluoride. All right, so when we're talking about ionic bonds, we need to balance the charges, which we sometimes refer to as oxidation state, of our particles of our ions. And so we're going to look really quickly at some oxidation states. You might want to annotate this on your periodic table in your data booklet, and then get these guys memorized. So oxidation states help us predict what charge a particle is going to have based on it wanting to be more stable. Okay, atoms don't want anything. They just tend to go toward a more stable configuration. So we're talking about how these atoms can get to be more stable by matching an octet rule or a noble gas configuration. So if I'm looking at lithium, lithium has 2 electrons in the first energy level, and then it's got that one sad little valence electron way out there all by itself. If lithium can get rid of that one electron through oxidation, lose electrons, oxidation, we can get rid of that one electron. Now this whole energy level is kind of gone, and our valence energy level is now this one, energy level number 1, that has 2 electrons, and this is a full energy level. Remember that energy level number 1 and equals 1 is an s orbital, and s orbitals only have space for 2 electrons. So this is a full valence energy level. Energy level number 1 is full at 2. This guy looks a whole lot like helium right now in terms of an electron configuration, which means that this lithium cation is quite stable when compared to that lithium atom that had that 1 valence electron. So we can give lithium a full energy level, which is in energy level number 1, the duet rule, not the octet rule. We can make it match helium, noble gases configuration, and it's more stable. We can do the same thing over here if I'm looking at like fluoride. So fluoride has 2 electrons in the first energy level and 1, 2, 3, 4, 5, 6, 7 in the second. If I can give fluorine 1 more electron, now it has 1, 2, 3, 4, 5, 6, 7, 8. We have met that octet rule, and fluoride, because this now is fluoride with a -1 charge, is going to have the same electron configuration as neon. It's more stable. This is good. And so the oxidation states that we can predict based on trying to get elements to become more stable because they will have full outer energy levels. Our alkali metals, column number 1, are most likely to have a +1 charge. Alkaline earth metals are going to have +2 charges. They've got 2 valence electrons they want to get rid of. When they lose those 2 electrons, they're going to have a +2 charge. We're going to skip the transition metals because they're kind of weird and they can flip their charges around. We're going to go all the way over to boron and aluminum. These guys are most likely to have a +3 charge. The guys under the metalloids, these are actually also transition metals, even though they're like in the P block. So just be careful with that. Carbon is really weird, and we're going to say like everything from +4 to -4. This is like the tipping point between positively charged particles and negatively charged particles. Nitrogen is most likely to have a -3 charge, oxygen's a -2, fluoride and the halogens are -1. Then our noble gases, they want to stay right where they are. We're going to give them an oxidation state of 0. Get these guys memorized. And let's talk about how, what properties exist in ionic compounds. So ionic compounds tend to be solids at room temperature. They have a lattice type structure. This means that we're going to have repeating patterns of alternately charged particles. Repeating patterns of alternately charged particles. Here's my negatively charged chloride, positively charged sodium, negatively charged chloride, positively charged sodium, negative, positive, negative, positive, negative, positive, negative, positive, and it just keeps going around and around and around. Repeating patterns of alternately charged particles is what a lattice is. Because of that lattice structure in ionic compounds, we have very high melting and boiling points, a very low volatility. It's very, very unlikely to turn into a gas. The solid ionic compounds, interestingly, do not conduct electricity very well, but if I make these guys crazy, crazy, crazy hot and they melt, if I have melted salt, it will conduct electricity. When I dissolve it in water, it also is really good at conducting electricity. Ionic compounds tend to dissolve quite well in polar solvents like water, because water has some partial charges, and that makes these charges kind of happy. They do not dissolve very well in nonpolar solvents like oil, again, just because of those charged particles. And then a little bit of vocabulary. So when we talk about covalently bonded things, we're going to use this word molecule. We really shouldn't use molecule when it comes to ionic compounds. This is not a molecule of sodium chloride. This is also not a molecule of sodium chloride. Sodium chloride is going to come in some ratio of sodiums and chlorides that are stuck in this lattice structure, and it might be like 100 to 100, or 1,000,000 to 1,000,000, or I don't know, 1,000,000,000 to 1,000,000,000. We're going to have some crazy large number of ions that are stuck in this lattice structure, but the ratio will always be 1 to 1, and so we talk about the formula unit. The formula unit of an ionic compound will be that lowest ratio of the particles. So for sodium chloride, Na1 to Cl1, even though we would never have just one sodium ion and one chloride ion. All right, let's look at naming some ionic compounds. So magnesium is an alkaline earth metal. It's going to have a charge of +2. Fluoride is a halogen. It's going to have a charge of -1. These are not matches. Our goal is to get these to balance each other out. Naming and writing formulae for ionic compounds is all about balancing the charges. And so to balance the charges, I need to get 2 of these guys, because 2 times -1 is -2, which will balance out that +2. And so my formula will be MgF2. Magnesium fluoride, change the end of fluorine to fluoride. Magnesium fluoride is the name of this guy. The formula is MgF2. Let's do the same thing for aluminum and oxygen. Aluminum has a +3 charge. Oxygen has a -2 charge. The least common multiple of 3 and 2 is 6. So if I have 2 aluminums, 2 times +3 is +6, and then 3 times -2, 3 times -2 is -6, and that balances out. So the formula for aluminum oxide is Al2O3. Change the end of oxygen to "ide." The first name, the metal ion name, does not change, aluminum, but then my non-metal anion changes to "ide" at the end, aluminum oxide. Sodium and oxygen. Sodium is Na, not S. Not S. S is sulfur. Sodium is Na. Na is going to have a +1 charge. Oxygen is still a -2. To balance that out, I need 2 of those sodiums. So my formula for sodium oxide is going to be Na2O. Calcium and nitrate. You're like, hey, this is not an element. You are right. It is a polyatomic ion. With a formula of NO3 with a -1 charge. I'm not going to change anything about that formula, but I do still have to balance out my charges. Calcium is a +2, nitrate is a -1. To get that to balance out, I need 2 of these guys. My formula is going to be calcium nitrate, but I need 2 nitrates. I'm going to put my nitrate in parentheses and put the 2 on the outside. Because if I didn't do that, if I just did NO3, now it looks like we have 32 oxygen atoms, and that doesn't make any sense. So calcium nitrate, don't change the name of the polyatomic ion. It's going to stay the same. Calcium nitrate, it will be CaNO3, NO3 in parentheses. Ammonium is our super weird positively charged polyatomic ion, and its formula is NH4 with a +1 charge. Phosphate is PO4 with a -3 charge. This is a -3, this is a +1. To balance that out, I need 3 of these guys. And so my formula will be NH4, 3 PO4. Ammonium phosphate. Again, do not change the name of the polyatomic ion. Ammonium phosphate is the name of this thing. Put ammonium in parentheses, NH4, 3. PO4 does not need parentheses because there's only one of it. All right, so now let's look at these guys that have some Roman numerals. Our transition metals do not, most of them do not have only one oxidation state, and so we're going to add Roman numerals to tell us the oxidation states of these guys. So copper 1 and oxygen, we're going to change oxygen to oxide. Copper has a charge of +1, oxygen has a charge of -2. To balance that out, I need 2 coppers. So Cu2O is going to be named copper 1 oxide. I need to keep that Roman numeral in the name because if I look at this guy, copper 2 and oxygen, this copper has a +2 charge. Oxygen still has a -2 charge. And I have CuO. No 2 necessary because these guys already balance each other out. This is copper 2 oxide. I need to keep those Roman numerals in the names so that I know that these are different compounds. Good. All right, let's do some more practice. Iron 3 and oxygen. Iron is Fe plus 3 charge, oxygen minus 2 charge. The least common multiple of 3 and 2 is 6. And so I'm going to give this a 2 and this a 3 because 2 times 3 is 6 and 3 times 2 is 6. My formula for iron 3 oxide is going to be Fe2O3. Lead 2 and nitrate. Again, I've got a polyatomic ion here. I'm not going to change the name, but I do need to make sure that I'm still balancing out the charges. So I've got lead with a plus 2 charge. Nitrate is NO3. It has a minus 1 charge. To get these guys to balance out, I need 2 of these. So my formula for lead 2 nitrate, don't change the name of the polyatomic ion, is going to be Pb parentheses NO3 2. Lead 4 nitrite, Pb is going to have a plus 4 charge. Nitrite, be careful, this was 8, this is ite. Nitrite is NO2 with a minus 1 charge. I need 4 of these minus 1 guys to balance out the plus 4 on this guy. And so my formula for lead 4 nitrite is going to be Pb NO2 4. Good? Good. All right, so we're going to flip over to some covalently bonded molecular compounds now. And instead of transferring electrons and making ions, now we're going to share some electrons. This usually happens between nonmetals. This graphic is just showing us that this electron of hydrogen and this electron of oxygen are going to end up as a shared pair, The magic of this is this hydrogen in energy level number 1, it wants 2 electrons. It now has 2 electrons. This hydrogen also now has 2 electrons. That first energy level is full. It's a happy, stable atom. Oxygen, draw a little bit of a Venn diagram here. Oxygen also in its outermost energy level has 1, 2, 3, 4, 5, 6, 7, 8, because that was a terrible color to choose. 5, 6, 7, 8. Because those electrons are shared, I get to count them for both atoms in the bond. And so now oxygen also has that full octet, full valence energy level, and everything is more stable because it's sharing those electrons. All right, let's name some covalent compounds. No balancing of charges necessary. Whoa. If I could spell balancing. No balancing of charge is necessary because we're not going to worry about charges for now. Instead, we're going to use our lovely prefixes when we name covalent compounds. If there's only if there's only one of the first element, then no prefix is necessary. And so this is going to be called carbon, just carbon. I'm going to add a prefix for the second element every single time. So carbon mono, because there's only one oxygen, monoxide. Change the end of oxygen to ide, carbon monoxide. This is almost the same. There's only one carbon, so no prefix is necessary for that first element, just carbon. But now I have 2 dioxide, carbon dioxide. I have 2 of the first element, so now I do need to give this guy a prefix. I have 2 nitrogens, so I'm going to call it dinitrogen. Notice that the first element name doesn't change. It stays the same at the end. We just might add a prefix. Dinitrogen, I do have only one oxygen, so it's going to be monoxide. Change the N to ide. NO2, there's only one nitrogen, so no prefix needed for that first element, but now I have 2 dioxide. Dinitrogen monoxide, nitrogen dioxide. H2O, you're like, that's water. Yes, but we also have a super fancy name for it in chemistry. I have 2 hydrogens, so dihydrogen. I have 1 oxygen, monoxide. Dihydrogen monoxide is also water. And then one more, P2O5. I have 2 phosphoruses, phosphori, if you will, diphosphorus. And I have 5 oxygens, pentoxide. Diphosphorus pentoxide is the name of this guy, P2O5. Memorize those prefixes. All right, so Lewis structures are all about valence electrons on particles, and we care about the valence electrons because these are the ones that are involved in chemical bonds. They are the most important electrons, the most important electrons because they are the ones that help to make the bonds. So if I were to draw a Lewis structure for lithium, lithium has 3 total electrons, but I only want the valence electrons, so I'm going to give it 1 dot. And that dot represents the 1 valence electron that lithium has. This is it, the Lewis structure for lithium. If I were to draw the Lewis structures for oxygen, oxygen has 1, 2, 3, 4, 5, 6 valence electrons, 8 electrons total, but only 6 valence electrons. Carbon has 4 valence electrons, and so for carbon, I'm going to show 1, 2, 3, 4. 6 on oxygen, 4 on carbon. Why I care about these Lewis structures is because now I can show how electrons are being shared. So carbon dioxide is CO2. Carbon is going to go in the middle because it's a singleton and it's also more to the left in the periodic table. And the guy that's more to the left in the periodic table is more likely to be in the middle. Since I have multiple oxygens, it's not going to be in the middle. We're going to put them around the outside instead. We're going to count our valence electrons. Carbon has 4, oxygen has 6, but there's 2 of them, that's 12. 12 and 4 makes 16 total electrons that I get to use in the bonds. So I'm going to count up all the valence electrons. Count all the valence electrons. Whoa, if I could spell valence. These are the guys that I'm going to use to make my bonds. Valence electrons only to make the bonds. I have 16 of them. We always work in pairs. So I'm going to put pairs between carbon and oxygen to get started. And then I'm going to start filling in octets. The goal is that everybody gets an octet at full energy level. So right now I've put down 1, 2, 3, 4 electrons. Let's do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so if I draw some lovely Venn diagrams, this oxygen right now, perfectly happy, it has 8. We're good. This carbon, not so happy, it only has 6. This oxygen, also not super happy, it only has 6. But I've used up all of my valence electrons. What we're going to do is make some double and triple bonds, perhaps. So I'm going to go back. I'm going to erase some things, and I'm going to make some double bonds. So instead of only 1 pair of electrons between carbon and oxygen, I'm going to add 2 pairs of electrons between carbon and oxygen. So now I have 2, 4, 6, 8 electrons all together. Carbon already super happy. Carbon has 2, 4, 6, 8. But I've only used up 8 electrons and I have 16 total to work with. So I'm going to add 2 more here. There's 10. Here's 12, here's 14, here's 16. Here are my 16 electrons, 16 valence electrons that I have to make bonds. If I look at oxygen now, and I make the Venn diagram to include all the shared electrons, he has 2, 4, 6, 8. 8 is great. This oxygen also, if I count the shared electrons, 2, 4, 6, 8. 8 is great. Carbon has 2, 4, 6, 8. 8 is great. Everybody is happy. And so this is the Lewis structure for carbon. You don't need to draw the Lewis dots, or sorry, you do need to draw the dots. You don't need to draw the circles. So you could draw like this. You could also add bars instead of pairs of dots. So you could do this, where each of these lines represents a pair of electrons, a pair of electrons. You could also, sometimes we like to get super fancy and show that the electrons of one element are X's and the electrons of the other are O's. If you want to add X's and O's, that's also an option, but not a requirement. All right, let's practice some Lewis structures for fluorine F2. So I have 2 fluorines. They're just going to have to be next to each other. Each of them has 7 valence electrons. There's 2 of them. That's a total of 14 electrons. We're always going to start with shared pairs in the middle. There's 2. Here's 4, 6, 8, 10, 12, 14. These are the 14 valence electrons that come from 2 fluorines that each have 7 electrons. And if I draw some lovely Venn diagrams showing those shared pairs of electrons, this fluorine has 2, 4, 6, 8. All is good. This fluorine also has 2, 4, 6, 8. All is good. So you can draw like this, or you can draw like this, or you could draw X's and O's. Oxygen. Oxygen has 6 electrons. There are 6 valence electrons. There are 2 oxygens. That's a total of 12 valence electrons to make bonds with. So if I start with oxygen and oxygen, I put a shared pair in between them. There's 2, 4, 6, 8, 10, 12. Oh no, I've run out of electrons. Whatever will I do? We are going to steal from one and make a second shared pair. So now I have 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, 2, 4, 6, 8 for this oxygen. Everybody is happy. This is a double bond. We have made a double bond. This is oxygen O2, double bond. All right, what about nitrogen? Each nitrogen has 5 valence electrons. There are 2 of them. That's a total of 10 valence electrons. For nitrogen, we're going to go N and N. I'm going to put a shared pair in the middle. There's 2, 4, 6, 8, 10. One of those nitrogens is very happy, the other one is not. So I'm going to erase, and I'm going to go like this and make a double bond. Well, this nitrogen has 8, but this guy still only has 6. Not good enough. We're going to steal again, and we're going to make, oh my goodness, a triple bond. 3 shared pairs of electrons. And now, notice that this nitrogen has 2, 4, 6, 8. 2, 4, 6, 8. This nitrogen also has 2, 4, 6, 8. Everybody's happy. And we can show that triple bond with 3 lines and then those other electrons that are not shared on the outside. All right, H and F, hydrogen fluoride. Hydrogen has 1 valence electron. Fluorine has 7. That's a total of 8 is great. So I'm going to have H and F. I'm going to put my shared pair in the middle. There's 2, 4, 6, 8. Oh no, should we make some double bonds? No, we're not. Our halogens will never, ever, ever make double bonds or triple bonds. And also remember that hydrogen is in my first energy level. Energy level number 1 only has space for 2 electrons. We don't have an octet rule, we have a duet rule. And so this hydrogen, this would never happen. Hydrogen would never have 8 electrons. So I'm going to leave just these 2 here. Hydrogen is already happy and stable. It's got those 2 electrons. My other electrons, to get to those 8 valence electrons, are all going to go on fluorine. Fluorine now has 8 and hydrogen has 2, and this is good. Hydrogen does not want 8. How I would draw this, HF, and show those electrons around fluorine, not around hydrogen. Good? Good. More Lewis structures. CH4, we're going to put carbon in the middle. We're going to put the hydrogens all around, just like that. I'm going to count up my valence electrons. Carbon has 4 valence electrons. Each of those hydrogens has 1. 1 times 4 hydrogens is 4. 4 plus 4 is 8. I've got 8 total electrons to put into some bonds. I'm going to put a pair between carbon and hydrogen, another pair between, another pair between, and another pair between. We always start with shared pairs between atoms. I have used up all 8 of my valence electrons that can go into bonds. But that's okay, because this guy is done. 2, 4, 6, 8. Carbon has 8. You might be thinking, but what about poor hydrogen? No, remember that hydrogen is stable at just 2 because energy level number 1 only has 1 s orbital and there's only space for 2 electrons there. So this is the Lewis dot structure for CH4. You can draw it like that with dots. You could also draw it with lines like that. Good? Good. All right, let's do NH3. Nitrogen has 5 valence electrons. Hydrogen each has 1. There's 3 hydrogens. 5 plus 1 times 3 equals I don't need to add any more, equals 8 electrons again. Nitrogen's going to go in the middle. Hydrogen is going to go around. Hydrogen never, ever, ever goes in the middle because it can only share 1 electron. I have 8. I'm going to start between. There's 2. There's 4. There's 6. Where do I put pair 8? I'm going to put it on the nitrogen because remember, all those hydrogens are already stable at just 2, at 2, at 2. But by giving nitrogen that unbonded pair of electrons, nitrogen now has 8. I can draw it with lines like this. Make sure that you add a bar to show that non-bonding pair of electrons on top of the nitrogen. All right, CCl4, carbon tetrachloride. Oh my gosh, so many electrons. Carbon has 4. Chlorine each has 7. 7 times 4 is 28. 28 plus 4 is 32 electrons. Holy smoke-a-ronies. All right, carbon's going to go in the middle. Halogens will never, ever, ever go in the middle because they do not like to share any more than 1 electron. And so I'm going to go ahead and start with bars. Remember that each bar counts as a shared pair of electrons. So I've got 2, 4, 6, 8. Carbon is now happy. Carbon's got all 8 of its valence electrons. Its outer energy level is full. But I have 32 electrons to work with. I've only used up 8. The others are going to go to the chlorine atoms. So again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All the magic. Everyone has 8 valence electrons. Because each bar, remember, is a shared pair. Well, shared if it's here, unbonding if it's here. Good? Good. All right, let's do NO3 with a -1 charge. This is nitrate. We can draw Lewis structures for polyatomic ions like nitrate. Same way. Nitrogen has 5 valence electrons. Each of those oxygens has 6. There's 3 of them. And then here's the quirky thing. This -1 charge means that this guy gained 1 extra electron. So I'm going to add 1 more to show that charge of -1. Total of 5 plus 18 plus 1, that's 24 electrons. Nitrogen in the middle, oxygens all around. I'm putting nitrogen in the middle because there's only 1 nitrogen and multiple oxygens. Also, nitrogen is more to the left in the periodic table, and the more to the left you are, the more likely you are to be in the middle instead of the outside of a molecule. So I'm going to start putting my shared pairs of electrons. I have 2, I have 4, I have 6, and 8, 10, 12, 14, 16, 18, 20, 22, 24. All those oxygens are good. Each of them has 8 valence electrons. The problem is nitrogen only has 6. And so we're not quite done yet. I'm going to steal a pair. It doesn't matter from which oxygen. I'm going to steal from this guy. And then I'm going to make that a double bond right there. So now this oxygen still has 2, 4, 6, 8. That oxygen is still content, but now nitrogen is also stable with 8. It doesn't matter where I put that double bond. I put it here. I could have also put it, that was a bad O, here. I could have also put it over there. Any one of those is good. And we'll talk in another lesson later about this idea of hybrid structures and resonance. And we'll talk about what we do when we can put double bonds in more than one place. But for now, pick a spot. Any spot. Any one is good. All right. So we looked at some times when we have to make double bonds and triple bonds. What's interesting about those bonds is that different bonds, single, double, triple, have different lengths and strengths. In our data booklet, tables 10 and 11 are going to give you those bond lengths and bond strengths. I put this one in the slideshow because it kind of puts everything into one table instead of multiples. So this single bond between carbon and oxygen has a bond order of 1. That just means it's a single bond. Its length is 143 picometers, and its strength, the energy needed to break that bond, is 358 kilojoules per mole of that bond. If I make it a double bond, now it's bond order of 2, notice that it gets shorter. And the reason is because a single bond, I'm only sharing one pair of electrons. So I have two electrons, I have the nucleus, I have the nucleus. We have some forces of attraction, electrostatic forces of attraction between the nucleus of carbon and that shared pair of electrons, the nucleus of oxygen and that shared pair of electrons. But if I do a double bond, now I have more electrons. There's 4 electrons. This is a bigger negative cloud of stuff. And so carbon's nucleus is going to be more attracted because the charge is bigger, 4 instead of only 2. So the bond gets a little bit shorter, and also because that force of attraction is greater, more energy is needed to break it. If I look at a triple bond, bond order 3, 1, 2, 3, now I'm sharing 1, 2, 3 pairs of electrons between carbon and oxygen. I have 6 electrons. It's more negative. That charge increases, which means that the attraction between the nucleus of carbon and that cloud of electrons, the nucleus of oxygen and that cloud of electrons, that attraction increases, which shortens the bond. And notice that the energy needed to break it also pops up a little bit. So again, if I have a single bond between carbon and oxygen, it's going to be pretty long, 143 picometers. Not a whole lot of energy is needed to break it. But if I make that a double bond between carbon and oxygen, the bond is going to get shorter. Double bonds are shorter and also stronger, more energy needed to break it. And then if I go to carbon monoxide, where I have 1, 2, 3, a triple bond, bond order of 3, the length is shorter and the strength is bigger. So shorter bonds, more strong. Single bonds, longer, less strong. All right, quick review, ionic versus covalent bonds. Ionic bonds form between oppositely charged ions, usually a metal and a nonmetal. We're going to transfer, lose or gain electrons. We still have an electrostatic attraction between those oppositely charged ions, the cations, the anions. Very high melting and boiling points, low volatility. Going to be soluble in water most of the time, and then they can carry an electric charge when they're melted or dissolved. That's different from our covalent bonds. Covalent bonds usually form just between nonmetals. Instead of losing or gaining, we're going to share. There's still an electrostatic attraction, but now instead of between those oppositely charged ions, it's between the shared pair of electrons, which are negatively charged, and the nuclei of the atoms, which are positively charged. So we have still attraction between opposites, but instead of ions being oppositely charged, now we have electrons and nuclei are oppositely charged. Instead of high melting and boiling points, we have low melting and boiling points. Instead of low volatility, they just don't, turn into gases. These guys can often easily become gaseous form. Most of them are not very soluble in water, and they don't have any electrical conductivity. So I'm going to talk a little bit about polar, nonpolar, covalent bonds, and it's all about electronegativity differences. Remember that electronegativity is that attraction for shared pairs of electrons, and in these molecules, we're looking definitely at those shared pairs of electrons. When we have a difference in electronegativity between two atoms that are sharing electrons, we have what we call a dipole moment. We'll talk a lot more about dipoles in a couple more days. But basically what happens is this. In a water molecule, oxygen is more electronegative than is hydrogen. And so the shared pair of electrons, instead of hanging out equally between hydrogen and oxygen, they are going to get pulled far, far, far more closely to oxygen. And so this extra little bit of negative stuff, because the electrons are closer to oxygen, makes oxygen partially, this is lowercase delta, partially negative. And because the electrons are closer to oxygen, less close to hydrogen, hydrogen is left to be partially positive. This sets up a little bit of poles. We say that water is polar because it has a positive side near the hydrogens and a negative side near the oxygen. Water has a dipole moment because it literally has two poles, a positive pole on the hydrogen side, a negative pole on the oxygen side. How do I know if something is polar or nonpolar? We're going to look at, this is the difference, the change in electronegativity. So I pull up the electronegativity differences. If the electronegativity difference is greater than 1.8, we're going to call this guy ionic, even if it's not metal, non-metal. That's really weird, right? But IB says if it's greater than a 1.8 electronegativity difference, it really is going to be more of an ionic set of properties than covalent. If there is no difference between the electronegativities of the two atoms in the bond, then it's going to be a nonpolar covalent or a pure covalent bond. Polar covalent bonds form if I have an electronegativity difference that's between 0 and 1.8. So if I'm looking at like carbon and hydrogen. Carbon's electronegativity is 2.6. This is table 8 in your data booklet, by the way, table 8. So carbon is 2.6 and hydrogen is 2.2. The difference between those two, and I only look at the difference in that single bond, the difference in this bond between carbon and hydrogen, 2.6, 2.2, is 0.4. 0.4 is between 0 and 1.8, so this is a polar covalent bond. If I were looking instead at perhaps nitrogen gas, now I'm looking at the bond between two nitrogens. Nitrogen is 3.0. Nitrogen is also 3.0. The difference is 0. The difference is 0. That's going to be a nonpolar or a purely covalent bond. Let's practice a little bit. Cl2. Cl is 3.2. Cl is also 3.2. The difference is going to be 0, and so this is going to be a pure or non-polar covalent bond. How about HF? Hydrogen is 2.2. Fluorine is 4.0. The difference is 1.8. What? 1.8? It's so different. It's almost ionic, but not quite. It is definitely polar covalent, but it's so polar, it's almost ionic. Crazy sauce. And then water, H2O. Oxygen is 3.4. Hydrogen is 2.2. The difference here is 1.2. The difference here is also 1.2. We look at the difference in each pair. This is a polar covalent bond. This is also a polar covalent bond because 1.2 is between 0 and 1.8. Good? Good. All right, we're going to look at acids and then we're finally done, my friends. I know this turned into a pretty long day. Hopefully you turned me on to extra fast YouTube speed. All right. How do we name acids? We have 3 different kinds of acids. We have some acids that are called binary acids. They are formed between only 2 elements, hydrogen and something else. Hydrogen and something else. Hydrogen and something else. These are binary acids. The rule for binary acids is we're going to call them hydro-something-ic acid. Hydro-something-ic acid. Since I've got chlorine here, this is going to be hydrochloric acid. Since I have fluorine here, this is going to be hydrofluoric acid. Since I have sulfur here, this is hydrosulfuric acid. If it's binary, hydrogen and only one other thing, hydro-something-ic acid. If I have more than 2, hydrogen and 2 other things, now I'm looking at my list of polyatomic ions. And we're going to call these guys oxy acids because they're always going to have some oxygen in them from the polyatomic ion. No hydro, no more hydro. Hydro is gone. Instead, polyatomic ions that end in 8 turn into ic acids. No hydro. Polyatomic ions that end in ite turn into us acids. This right here is nitrate. 8 turns into ic. So when I take nitrate and I put a hydrogen in front of it, it turns into nitric acid. This is sulfate. The polyatomic ion sulfate. 8 turns into ic acid. And so this is going to be sulfuric acid. Notice no hydro. Hydro only if it's binary. No hydro if there's a polyatomic ion involved. All right, over on the other side, this is nitrite. Nitrite. Ite turns into us. This is going to be nitrous acid because I put a hydrogen on an ite polyatomic ion. This is sulfite. When I throw some hydrogens in front of sulfite, it turns into sulfurous acid. Ite to us, ate to ick. Memorize that. Happily, it kind of goes in alphabetical order. So ate, ick, ite, us. Remember that it goes in alphabetical order. Ate turns into ick, and ite turns into us when you have polyatomic ions with hydrogens in front of them. Good? Oh my gosh, we did it. We defined ions and ionic bonding, and we talked about how to name those guys. We reviewed covalent bonding and how to name those guys. We drew some Lewis dot structures to show shared pairs of electrons. We talked about how single bonds are long and weak, triple bonds are short and strong. We had that table comparing, contrasting ionic and covalent bonds. We talked about electronegativity differences. We're going to talk a lot more about that in our next 2 lessons. We reviewed acid nomenclature. We did it. So proud of you, my friends.